So what happens if we have multiple different mutable functions? Well, let's find out. Okay, so we'll keep the code the way it was before. And we'll create two bank accounts. Let's say John starts with $20 and Steven starts with $100,000. So if John withdraws $1, then he has 19 left. And if Steven withdraws $1,000, then he has $99,000 left. Now what about poor John? John still has, let's withdraw 0 just to figure it out, still has $19. So Steven and John have different bank accounts, right? They don't interact in any way. Because we're not using any global names. Instead, each of these two functions, John and Steven, is a different function. We can tell that because it has a different number here. And they're different because they have different environments. So the non-local frame for John has balance bound to 19. And so when John tries to withdraw $1,000, he is broke. But Steven can withdraw $1,000 many times over and be just fine. Because the different environments keep these two things separate. So this is the whole point of mutable functions, is that they keep the state that's relevant to evaluating that function local to that function. It's part of the function itself. And it doesn't interact with other parts of the program. And that's very convenient because it allows you to build pieces of a program that know about their own data, but manage it effectively without interacting in strange ways with other parts of the program. So let's talk about sameness and change. As long as we never modified objects, we could regard compound objects to be precisely just whatever their pieces were. So example, a rational number is just a numerator and its denominator. But this view is no longer valid in the presence of change. So you could have two different bank accounts with the same balance, but they're different in that if one changes, the other does not. So a compound data object has an identity now, something more than the pieces by which it's composed. A bank account will still be the same bank account, even if we change the balance. But we could have two bank accounts with the same balance, but they're different objects, meaning withdrawing from one doesn't withdraw from the other. So now we have to worry about whether two things are equal, as in the equal number, and whether they're the same or not. And we saw this issue pop up when we were looking at lists. So the important thing is that John's account and Steven's account are different objects, even if they have the same balance. So if we switch back to our example, Steven has $95,000 left. John has 19. So let's say Steven actually spent $94,981 of his dollars. So now Steven and John both have the same balance. If we look at that balance, we'll find that they're equal. However, this Steven's bank account is not John's bank account. They're different objects. We saw that they're different objects because they printed out slightly differently, but is and is not are operators to actually test whether two things are the same or not. Whereas John is in fact John, and if I give John a different name, such as John's account, then John's account is still John. They're just two different names for the same thing, which means, okay, so just put this at the top of the screen, which means that if I withdraw from John account, and then I withdraw from John, I'm really withdrawing from the same account twice over. But Steven still has $19 left. Now there's consequences to having mutable data. We've lost something. It's something that you might not have even known we had, but it's actually an important property. So expressions are referentially transparent if substituting an expression with its value does not change the meaning of the program. Here are some referentially transparent expressions, and notice that they involve calls to immutable pure functions. So if I multiply the result of adding 2 and multiplying 4 and 6, then we're multiplying that with 3 plus 5, that's the same thing as if I evaluate this, but I replace mul 46 with its value 24. That's referential transparency. And likewise, I could replace add 224 with its value 26. Again, referential transparency. And so we can think about this complex thing as just being another way of writing this simpler thing, and we could evaluate it in pieces like that. But mutation operations violate the conditions of referential transparency because they do more than just return the value. They change the environment. So if add changed the environment, then it wouldn't be the same thing to say add 224 or just 26. So mutation does not allow referential transparency. Okay, let's look at one more example. This is one where you should try to think through what happens yourself. So I'll show you the beginning of the environment diagram. Is that we have a higher order function f, we call it on 1, which binds x to 4, and then defines g and returns that. And then we call g, which defines h and returns that. So now we have functions a and b with two different parents, and what we're going to evaluate is b3 plus b4. So think about it before going on in the video. So what happens is that we evaluate b3 first. So b3 is a call to h, z is bound to 3, we declare x as non-local, and then we change x. So x is going to change way up here in the non-local frame. So now x is 5 instead of 4, and we'll return x, y, z. Well, what's x, y, and z? Z is here is 3, y is 2, and x is 5. So the total is 10. So we return 10, and we've evaluated b3 is 10. And now we have to go through and evaluate b4. So we bind z to 4 this time in this second call to h, which has the same parent as the first call to h. We increment x way up here, and then we add x, y, z, so that's 4 plus 2 is 6, plus another 6 is 12. So 10 and 12 together is 22, which I forgot to bind it to a name, so it doesn't show up in the environment diagram, but you would get 10 plus 12 is 22, which is different from if I had just replaced this with the number 10, at which point x would be 1 less than it was before because b would not have been called in this case, and the answer would be 21. Referential transparency was lost.